So now what we're going to do is I'm going to go over some problems, specific problems dealing with the 5 different gas laws. The ideal gas law, Boyle's, Charles, Gay-Lussac's, and Avogadro's, and how to apply them. And this is what you'll have to do. Well, there'll be a quiz that relates to these, and you'll have to do some problems using these, and it'll be a multiple choice. So here we go. All right, before we start using the problems, what we have to do is get some grasp of the units that we're going to be using, so that you get a general idea of what you're actually looking at. So it's just not a bunch of numbers and words that don't seem to have any meaning. And so what I'm going to do, first of all, I'm going to look at the 4 different variables: volume, temperature, pressure, and number of particles, and see what to expect and maybe how you can relate to them in the world that you live in. All right, so let's look at volume first of all. So volume is length times width times height, and it could be measured all kinds of ways. All right, one way that you can measure it is like cubic feet, cubic inches, and typically, like if you had a cubic feet, it'd be like feet to the 3rd power, or cubic inches. And what that means is it measures some cube and how much space can be in that cube. But there's other ways to measure volume as well. You may have heard of gallons and quarts and things like that. So typically in science, we don't use these units here. We use something called liters and milliliters. And I want to give you some sense of what liters, milliliters, and all that are related to some things that you've seen in everyday life. Okay, so a liter, 1 liter, is approximately equal to 1 quart. Okay, so a liter is also about 1,000 it is 1,000 milliliters. Okay. All right. So this is good. So if you have a quart of whatever, okay, it's about 1 liter. All right. So based on this, okay, if you have half a liter, okay, what is that going to be? Well, what's a half quart? I'm not sure if you guys know this, but it's a pint. Okay. And half a liter is 500 mils. Okay, so I'm right now looking at a bottle of Diet Coke, and on the side of it says it has 500 mils in it. But it also tells me it's about 1.06 pints. And it also tells me that it's about 16 ounces, okay? So if a pint is 16 ounces, then a quart is 32 ounces. All right, now, so if you go down further, okay, so if you have half of a half or a quarter of a liter, okay, well, that's going to be 250 mils. Okay, mils. And how many ounces is that? 8 ounces. And what is 8 ounces? 1 cup. Okay, now, if you remember, you guys haven't seen it, but if you just go and get yourself a coffee cup, that's 1 cup, and that's approximately 250 mils. So if you had 4 of those, okay, you would have 1 liter about. Okay, now going the other way, if you have 4 quarts, okay, is equal to what? It's equal to a gallon. Okay, which is approximately equal to 4 liters. All right. And then that's 4,000 mils, approximately. Okay. Now, actually, it's 3.785 liters per gallon, but you don't have to know that exact, but you just roughly, 1 gallon is roughly equal to 4 liters. And so if there's if there's a problem and it says there's 2 liters, you can go, oh, that's like a half a gallon or 2 quarts. Okay. So that's I just want to put this in perspective, because we use liters, milliliters, and be nice to be able to understand how it relates to. Okay, now let's look at pressure. Okay, so pressure can be measured in different ways. You may have seen pressure, heard of it like your air pressure in your car or your tires in your car is PSI. And what that stands for is pounds per square inch. Okay, so what that means is for every square inch, how many pounds are being applied of gas on that inch of area. Okay, you don't have to know that, but so PSI is a measure of pressure. And it turns out that barometric pressure, the amount of pressure that's actually around us, touching us, pushing against us all the time, is actually about 15 pounds per square inch. Okay, now to put this in perspective, the top of your head, so your head, let's say your top of your head's a square, all right. The top of your head is approximately 5 by 5, so it's about 25 square inches on top of your head. Okay, and then for every square inch, you have 15 pounds against it. All right, so when you do the math, on top of your head, there's 375 pounds being pushed on top of it. Okay, that sounds like a lot, but the good thing is your skull and the rest of your body are pushing out with the same amount of pressure, and so you don't realize you've got 375 pounds on your head. All right. Okay, so there's other ways of measuring pressure, other units. I don't know if you pay attention to the weather or not, but if you hear the weather person, they'll talk about the pressure is 30 something, okay? And they'll say the pressure we are going to have, the barometric pressure is decreasing, and usually if it decreases, that means we can get rain. If it increases, it's going to be a nice, clear day. So, and they'll say around 30 when it's normal, okay? The units for that, and you don't have to remember this, but just know that this is they'll say 30-inch. If they say it all out, they'll say 30 inches of mercury. Well, it turns out these two things mean the same thing, but in different units. Okay. All right, and then because the rest of the world uses meters and things like that, this 30, because the rest of the world doesn't use inches, they use meters and millimeters. You could see a similar relationship is 760 millimeters of mercury. Okay, and these all are saying the same thing. These two things are just another way of saying 15 pounds per square inch. Okay, and then in chemistry, we have our own unit. We have something called atmospheres, ATM we call it, to give it a small unit. And it turns out that 1 atmosphere is about the same as 1 psi. So if I say I measure let's say the pressure is 2 atmospheres, that's going to be 30 psi. Now you're not going to have to do any of conversions, but I just want to have you understand that these numbers, if you say 30 inches and 15 pounds, it's not just some random something that doesn't make any sense. All right, and then in physics they use another value, and that's called kPa. All right, and approximately 100 kPa is equal to 1 is equal to 15 pounds per square inch. Okay, so you're not going to have to do any conversions, but let's say just let's just do it intuitively. Let's say you have 100 kilopascals and you change it to 500 kilopascals. All right, so what is this in terms of PSI? Okay, well, every one of these is 15. You increased it by 5, so now this would be 75 PSA, 5 times 15. Okay, you won't have to do that, but that's the kind of thing you should keep that in mind. Okay, next one is number of gas particles, and this is the moles. You really won't have to do anything with this. Just know what a mole is. It's, you don't have to know exactly, but just know it's a quantity of particles, and you can figure out the number of particles if you have the grams. Okay, so it turns out when we use these gas laws, whenever we have N, we could use moles as units or grams. That's if the gas that we're using is the same gas. So some of these equations you might see moles, and sometimes you may use grams. So whenever you see N, it'll either be moles or grams. Typically, it would just be moles. And the final one is temperature. And temperature is a little odd, and we have to be careful about it. Okay, and that's because you can have negative temperatures. So let's go over some ways that we look at it and how the rest of the world looks at it. So in chemistry, we use degrees Celsius. But we use Fahrenheit, and you guys should really should see how these two relate to each other. And I'll just go over some relationships between these. Okay. So I'm just gonna write. So the conversion is that Fahrenheit, and you don't have to do this. I'm sure you've seen this in math before. Is that okay, 32 plus 1.8 times Celsius will give you your Fahrenheit. What I like to do is just to come up with a rough value is take 30 plus 2 times Celsius, and I can get a real close value for my Fahrenheit. Okay, so let's go over some examples. So, all right, so it's 0 degrees, so let's say Celsius and Fahrenheit. Okay, so let's look at some relationships between at 0 degrees Celsius. That's 32 degrees, and that's where ice freezes. All right, and that's how they come up with this equation up here, by the way. At 10 degrees Celsius, if you plug this in up here, it turns out that that's 50 degrees Celsius. All right. Now, 20 degrees Celsius is approximately 70. It's actually 68. Okay. And so this is approximate. And this is room temperature. And usually when we do experiments, we'll have the temperature somewhere between 20 and 25 Celsius, which will be between 70 and 75 degrees. Okay. So this is a pretty important value here. So this one's important, and this one's important. Okay. So is the other relationship at 37 degrees Celsius. Turns out that's 98.6, and that's body temperature. Okay. So this is important, especially if you're going in the medical field. You may hear, especially if there's a lot of doctors that are from other parts of the world, then they learn body temperature in terms of Celsius, and they go, what's temperature? If you say 98.6, they might freak out, okay, because that you'd have a dead person. They'd blow up, all right? They're too hot. You may want to say 37. Okay, 4 degrees is about 105 degrees, and that would be hot outside. Okay, 50 degrees is about 150 degrees, okay? Or 140 degrees. And then 100 degrees Celsius is 212, where water boils. And you can see that both these values, 0 and 100, is determined by what happens to water. Just some other points. Minus 10 is about 10 degrees Fahrenheit. So minus 15 is about 0 degrees Fahrenheit. Minus 40, turns out, Celsius is where they are equal. Okay. All right. So there's just some relationships here. Your refrigerator is actually a big deal. Your refrigerator is at 4 degrees Celsius, which is 40 degrees Fahrenheit. And that's an important value. So the refrigerator is not some random number. It's set at 4 degrees Celsius, 4 degrees Fahrenheit, and that's because water is dense. It's most dense at that values. Okay, so now the problem with both of these, Celsius and Fahrenheit, is they have negative values. And when we do the gas laws, that's going to turn out to be a bad thing, especially when you have Charles' law and Gay-Lussac's law. So, like Charles' law, it turns out if you use Charles' law and you use Celsius to Fahrenheit, so Charles' law looks at volume and temperature. Okay, it turns out that if you use Celsius Fahrenheit, you could end up with a negative volume. All right, and there's no such thing as a negative volume. The lowest you can have is no volume, 0. You can't have a negative volume. So these two units aren't good. So what we have to do is have a unit for temperature that is doesn't have negative values, and that's called Kelvin. Okay, and we'll give it K. And Kelvin, it's named after Lord Kelvin, some guy, English guy back in the 1800s. And it's a real easy conversion, and you're going to have to be able to do this. This is the one conversion that the Kelvin is equal to 273 plus Celsius. So if we were at 0 degrees Celsius, we're at 273 Kelvin. If you were at 100 degrees Celsius, we would be at 373 Kelvin. Now you're going to have to do this conversion when you use Gay-Lussac's law, Charles' law, and the ideal gas law. The other two, Boyle's and Avogadro's, you won't. All right, so now let's get into doing some problems. All right, the first problem, and we're going to take a look at Boyle's law, we'll do a couple examples, is that we have a pressure of 405 kilopascals. Now, let's just go back to what I said, just so you can get an idea. Is that 405 kilopascals. If you remember, 100 kilopascals is equal to about 15 pounds per square inch. This is 4 times this, so this is about 4 times 15. So this is about 60 pounds per square inch. You don't have to do anything with that. I just want you to get I deal with that. And the volume is 6 centimeters. Now, the key thing with Boyle's law, you don't have to do any unit changes, okay? You keep the units kPa and centimeters cubed. All right, so this is our initial, this is our beginning, so this would be P1, and this would be V1. All right, so we're going to assume the temperature is constant, and now what we want to do is what is the pressure, so what is P2 if now the volume is 4? Okay, so here's my equation, here's P1, V1, and V2, and what I want to do is solve for P2. So what I'd like to do is I'd like to take our initial equation here, all right, and this should be a 2 here. So here, and I take my initial equation here and do simple algebra, and what I want to do is solve for P2. So I divide both sides by V2, and I get this equation. And then I plug everybody in, all right? So P1 is 405, V1 is 6, got my units, V2 divided by V2, 4. If you do it, these centimeters cancel out, it'll end up with kPa, do the math, and you get 607 kPa. All right, here's the next problem. So now we have atmospheres, and we have centimeters cubed. Okay. Volume, so volume 1 and pressure 1. All right, now I'm going to change, so I want to know what V2, what is V2 when pressure is increased to 1.9. Well, let's think about this. So what I want to do is I want to increase the pressure, all right? So I want to increase the number of collisions, all right? So what am I going to do with the volume? I got to shrink the volume. So this is an inverse relationship between pressure and volume. So I want you to know that, all right? I want you to know that for Boyle's law, it's inverse relationship. As you change one, the other one changes in the other direction. All right, so we plug everything in. Here's my equation. And again, this should be a 2. So I get, here's my 3 knowns. Rearrange my equation for V2. So I divide both sides by P2. And then plug everything in. Okay, and I said I thought I would need to decrease the volume to increase the pressure, and you can see that's true. Okay, it went from 326 to 189. All right, now let's do Charles' law. So Charles' law is the relationship between temperature and volume. They're directly proportional. So as you change one, the other one will change in the same direction. So if you increase temperature, the volume will go up, and the other way around. Now, here's what we got to do is that if you have Celsius to do this, you got to go to Kelvin. Okay, you can't do this in Celsius. You got to do them in Kelvin. So let's see what our problem has. So as I'm at 31 degrees Celsius, and it has a volume of 32.0 centimeter cube. What is the volume? What volume does the gas have to occupy at 11 degrees Celsius? So I have T1, okay, and I have T2, and I have V1. All right. So what I'm going to do is I need V2. All right, and we'll get to that in a second. But first thing we have to do is we have to get T1 in terms of Kelvin. So to do that, we and T2 as well. So it's simple. So 273, and it's 0.15, but you can leave the 0.15 off. So it's 273 plus 31, 304, and 11 plus 273, 284. So this is our T1, and this is our T2. All right, now the next thing before we get to our manipulating our equation. So here, what we did is we decreased the temperature, which have the volume. The volume should go down. All right. So we're decreasing the volume. I mean the temperature. So the volume should go down. So hopefully our answer will show that. So the volume should be less than 32. Okay. So temperature decreases, volume should also. So this is the equation. So this one, the only one that has the numbers on the same numbers on both sides would be Boyle's law. So T1 V2 equals T2 V1. All right. And what we want to solve is for V2. So divide both sides by T1. And you get this equation here. All right. And then you plug everybody in. Okay. Make sure you don't use Celsius, that use Kelvin. And you get 30 centimeters cubed. And you notice that's less than we started with, and that's what we expected. So good job. All right, Charles' law number 2. Okay, so this one's going to take a couple steps, so we got to pay attention to it. So we say our initial volume, so the V1, and our initial temperature is 25 degrees, and our final volume is 945. So we increase the volume, so we'll have to increase the temperature. Okay, so what we need to do this to figure, so we want to find out T2. All right, so we need to have temperature in Kelvin. So add 25 to 273, and you get 298. Right, you have your equation. Okay, and now what we want to solve for is for T2. So divide both sides by V1. And then plug everybody in. Okay. And here you get 331. And we said that if the volume goes up, temperature has to go up, and it has. But there's a little extra part to this. Now what we want to do is we want to get this to Celsius. Okay. Now to go the other way, so going from Celsius to Kelvin, you added 273. But going the other way, you subtract 273. So subtract 273 from 331, and you get 42 degrees Celsius. Okay, pay attention to what I just did up there. Go over it and make sure it makes sense. All right, Gay-Lussac's law. And Gay-Lussac's law is a relationship between pressure and temperature. If you increase one of them, the other one's going to increase as well, or vice versa. Again, in this one, if you have a Celsius, you got to go to Kelvin to do the equation. Okay, determine the pressure change when a constant volume of gas at 1 atmosphere is heated from 20 to 30 degrees Celsius. Okay, so my initial, so this is P1, this is T1, and this is T2. And I want to solve for P2. Okay, before I can do anything, I have to make sure my temperatures are in Kelvin. So I add 273 to both of them. Okay, so I increase the temperature, I expect the pressure to go up. All right, here's my equation, and I want to solve for P2. So divide both sides by T1. I get this. And plug everybody in. So P1 is 1 atmosphere. Initial temperature, final temperature is 303. Final initial temperature 273. Do the math. And you get 103 atmospheres. And that's what you expected. You expected the pressure to go up. That should be 1.03, sorry. All right, there you go. All right, no, the Gala X. Initial pressure is 0.5 atmospheres. The initial temperature is 25 C. The pressure's changed to 0.61. This should be atmospheres. And so what would the temperature be to increase the pressure? So it's gonna have to be you're gonna have to increase the temperature from 25 to something. So it's gonna be higher than 25. But first thing we have to do is change temperature to Kelvin. Add 273, you get 298. The initial temperature is the initial pressure is 0.5. We're increasing to 0.6. So we expect the temperature increase. So there's an increase. So we expect to have an increase in temperature. I want to solve for T2. And then what I'm going to do is I want to have the answer in Celsius, not Kelvin. So first thing I do is find it in Kelvin, and then change it to Celsius. All right, so I have there's my equation, and now I want to solve for T2. So I got T2, so I divide both sides by P1, and so I get 0.61 times 298 divided by 0.5, and that'll be about 364 Kelvin. Okay, so that's the answer in Kelvin. Now I want it in terms of Celsius, so I need to subtract 273. And I get 91 degrees Celsius. Okay, so to get the pressure from 0.5 to 0.61, I had to increase the temperature from 25 degrees Celsius to 91. All right, ideal gas law. All right, for the ideal gas law, the units you have to be concerned with units. N will always be in moles. Okay, pressure will always be in atmospheres. So if I ask you for pressure, if a question asks you for pressure, you're going to have to answer atmospheres, not PSI or whatever. Volume is always going to be in liters. And temperature can either be, it's always going to start out as Kelvin, but it could end up in Celsius or vice versa. Okay, but you can use the equation only when it's Kelvin. Okay, so there's no going to be change either here. You're not going to see like the volume changing or the pressure changing. You're only going to have to find one of the variables based on the others. Okay, so you have N, which is 4, and we're going to leave the units off because I said the units are always going to be the same. Okay, the only one you have to worry about is temperature, maybe. Okay, pressure is going to be 5.6, and volume is 12. Okay, and what we want to do is solve for T. All right. So here's our equation. So what we do, solve for T, we divide both sides by NR. And we get this. Okay, now R. What is R? As long as these units are what they are, your R is going to be equal to 0.0821. And I'll give that to you. Now, you don't have to worry about the units. It'd be great if you could figure out the units, but they're kind of tough, okay? They just -1 and all that. So I just want you to do the math. Key thing is the units. If the units are all these guys, then it's okay. Not worry about units. So you take 5.6, which is the pressure, 12, which is volume. Sorry about that. And divide by 4, which is the moles, and also divide by the universal gas constant. And when you do that, you get 205K. All right, and here's this shows you how you can get the units, but don't worry about this. All right, so so the units for temperature will be K as long as you have all of these guys right. Okay, here's the next one. So if I have an unknown quantity of gas, so that means I'm going to find quantity. So I have to find N, and the answer is going to be in moles. Pressure is equal to 1.07. I'm in the right units. It has the atmospheres. Volume is 0.312 liters. Okay, it's the right units. And temperature 87. It's in the wrong units, but it's easy to fix. Add 273. So it's 360. So temperature is now 360, and now I can plug it in. All right, I want to solve for N, so here's my equation. I divide both sides by RT, and then plug everything in. So I get 1.07. You don't even have to worry about the units, but you know that it's going to be moles. So 1.07 times 0.312 divided by 0.0821. Divided by 360, and your answer is 0.0113 moles. Don't forget your units. Finally, Avogadro's law. And Avogadro's law says if you change the number of particles, the volume's got to change in the same direction. So if you decrease the number of particles, the volume would have to decrease as well. All right, there's no temperature, so you don't have to worry about changing the temperature. So you can just leave the units the way they are. Okay, so 25.5 is your initial volume, right here. Your initial volume is number of particles is 3.5. Okay, now so the balloon leaks, okay, so it starts out at 3.5, and then it leaks 1.9, so then when you get done, it only has 1.6 moles. Okay, what happens to the volume? Well, you can tell it got smaller. It's like letting air out of a balloon, okay? And in fact, it is. That's what the problem says. All right, so we can figure out the volume. So here's our equation, and we want to solve for V2, so divide both sides by N1. We get that, then plug everybody in. So 1.6 times 25.5 divided by 3.5. And if you notice, units cancel out, and you get liters, and volume has decreased. It's gone from 25 to 11.6. It's good to see that the numbers work out how you expect them to. Okay, so here's the last problem. So there's some girl or fella named Sally, and has 3.13 moles of argon in a 5.29 liter balloon. So 5.29 liters, and inside is 3.13 moles of argon. Okay, and then what happens is they add 2.51 moles. So what happens inside the balloon? Well, it's going to get bigger. Got more particles, it's going to get bigger. So now the new number of particles is going to be 3.13 plus 2.51, or 5.64. Now what we want to do is find out the final volume. Okay. Okay, so we have the initial volume. We have our initial N. We have our final N, and we can find out our final volume. So here's our equation. We want to solve for V2, so divide by N1. Okay, then we plug it in. Okay, 5.64 is our final, is N2. 5.29 is our initial volume, and our initial number is 3.13, and the answer is 9.53 liters. Okay, and you can see this number is bigger than the 5.29. And why is that? Because you added 2.51. And does that kind of make sense? Well, this is, you're almost doubling, okay, the number of particles, so you expect it almost go up to about 10, and that's what you expect. All right, so that's it for the gas laws. On the test, there'll be five problems, one for each law, and you're just gonna, I'll send it the problem out, the test out to you. You're gonna have to do it, and then you're gonna have to answer questions on a quiz that deals with it. All right, so that's all. Okay, and that's it for the semester. Unless I've taught this earlier in the semester, but this semester it's the last thing, and